My name is Leonardo Antonino. I'm a doctoral student of UFABC Post-Graduate Program in Nanociência and Advanced Materials, and today I will present some results of my study, namely the synthesis of lignin-containing polyurethane thermoactive adhesives via hindered urea intermediate route. My presentation is divided into 5 sections: introduction, goals, methodology, results and discussion, and partial conclusion and next steps. Let's start with a brief introduction. Recently, the interest in renewable sources is growing, as can be seen in this graph. That shows the number of publications concerning lignin, cellulose, and starch, 3 renewable materials, per year in the last decade. But why? First, because of the imminent depletion of fossil fuels, and second, because of environmental issues. So, a possible solution for these problems is replace totally or partially no renewable source by renewable ones. In this context, lignin has been stained out. Lignin is a aromatic bipolymer found in lignocellulose biomass. It's the second most abundant bipolymer in the world. Here, a lignin generic structure is depicted. Okay, but why has lignin been stained out, as I mentioned before? Well, lignin has interesting characteristics, such as worldwide industrial viability, since it's a byproduct of some industrial process, stiff structure, and chemical polyfunctionality. Since there are diverse functional groups in lignin structure, such as hydroxyls, which has the predominant, and carboxyls. However, nowadays only 2% of world lignin production is converted in high added value materials. The remainder is burned for electricity generation. Now let's talk about polyurethanes. Polyurethanes are a versatile class of polymers conventionally synthesized from polycondensation between polyols and diazocyanates. Usually the polyols employed are petroleum-based ones. Since lignin is rich in hydroxyl groups, as previously mentioned, then lignin can replace petroleum-based polyols in PU synthesis. But in the context of PU synthesis, lignin has some limitations. These limitations can be overcome by chemical modification, as for example hydroxypropylation, and by the use of chain extenders, such as vegetable oils like castor oil. Now let's show the study goals. The study's goals are develop for the first time polyurethane thermoactive adhesives using lignin and castor oil as polyols via hindered urea intermediate route, contribute to lignin revalorization, and finally investigate the effect of 2 different hydroxypropylation reactions on final properties on the PU's thermoactive adhesives. Okay, let's talk about the methodologies employed. The first one regarding the hydroxypropylation of lignin with propylene oxide. Initially, crepe lignin was solubilized in a sodium hydroxide solution. When lignin was totally solubilized, propylene oxide was added dropwise in the solution. The mixture was kept at 40 degrees for 18 hours under magnetic stirring. After 18 hours, the product was precipitated in hydrochloric acid solution, vacuum filter, washed and dried at 8 degrees for 24 hours. The resulting modified lignin, called the HKL-PO, were characterized by FTIR, protonuclear magnetic resonance, in the SEC. A simple reaction scheme is represented here. Now let's see the methodology used in the hydroxypropylation of lignin with propylene carbonate. At first, crepe lignin was mixed with propylene carbonate in DBU catalyst. The result solution was kept at 170 degrees for 3 hours under nitrogen atmosphere. After 3 hours, the product was precipitated in hydrochloric acid solution, vacuum filtered, washed and dried at 40 degrees for 24 hours. The result modified lignin called 8-KLPC were characterized by FTIR, protonuclear magnetic resonance, and DSC. A simple reaction scheme is shown here. Finally, we have the PU Thermoactive Adhesives preparation methodology. This methodology is divided into 2 steps. The first step is prepolymerization, where initially polyol systems were obtained by mixing unmodified or hydroxypropylate lignins and castor oil in different lignin and castor oil mass ratios. After MDI and the nasocyanide blocking agent diazopropylamine were added to the polyol systems. The resulting systems were mechanically mixed for 10 minutes, and then PU prepolymers were obtained. The prepolymerization kinetics was investigated by FTIR. The second step is prepolymer curing. The PU prepolymers was heated until 100 degrees and were kept at this temperature for 24 hours. During the curing process, release of diazopropylamine was observed. The curing kinetics was investigated by temperature-modulated optical refractometry, and the PU adhesives were characterized by DSC, dynamic mechanical analysis, lab shear tests, and scanning electron microscopy. Now we will show and discuss the results. Unfortunately, in this moment, I just have lignin structural characterization results. Okay, let's start with FTIR results. Comparing the FTIR normalized spectra obtained for a modified hydroxypropylate lignin, some differences were observed. First, in the region between 3000 and 2800, the emergence of new peaks and an increase in the intensity of existing peaks were verified for modified lignins. This can be assigned to methyl, methylene, and methine groups of hydroxypropyl units attached to the lignin structure after the modification. Also, for modified lignins, the peak centered in 1120 was more intense. This peak is associated with stretching modes of ether linkage. Then this increase can be attributed to ether linkage formed from hydroxypropylation reaction. Furthermore, a peak centered in 1719 was only observed for HKL PC sample. This peak is assigned to carbonate linkage that can be formed from the reaction between aliphatic hydroxyls of lignin and propylene carbonate. Then we can affirm that there are strong evidence of modification. Now the protonuclear magnetic resonance results. Slightly differences were noted when comparing the obtained spectra. The most remarkable was the emergence of new signals between 1 and 1.5 ppm. Since this region of spectrum is associated with metal protons, then the new signals can be assigned to metal groups of hydroxypropyl units. An intensity increase in the signal closer to 3.5 ppm was also observed for 8KL PC sample. This increase in intensity can be assigned to methylene and methine groups of hydroxypropyl units. This intensity increase was not verified for 8KL PO sample, probably due to the inadequate sample preparation for NMR analysis. Lastly, a new signal appears closer to 2 ppm only in 8KL PC spectrums. This signal is still unknown, but probably associated with protons nearby carbonate linkage. Therefore, there are also evidence of modification. Finally, we have the DSC results. The DSC results showed a reduction in the lignin glass transition temperature after chemical modification. As already known, hydroxypropylation adds hydroxypropyl units into lignin structure. This addition causes an increase in steric hindrance between lignin polymer chains, and thus an increase in the free volume. Consequently, the molecular mobility of lignin is enhanced and a decrease in lignin Tg is expected. So, once again, there is a strong evidence of modification. To finish the presentation, I will present the partial conclusion and the next steps of my study. My study partial conclusion is lignin was successfully modified. The next steps will be investigate the pre-polymerization and curing kinetics of PU thermoactive adhesives and, if necessary, establish the best experimental condition and synthesize and characterize the PU thermoactive adhesives. Before end, I would like to thank UFABC for the funding support, UFABC and SEM for experimental support, and Professor Matilda and Danilo for our support along the discipline. Here's the reference. That's all. Thank you